In Chapter 18, we'll begin to look at reactions that benzene and aromatic compounds will undergo. So the first question we want to ask is, how will benzene react? And to figure that out, we need to think about, is benzene electron rich or electron poor? Does it have a lot of electrons or does it have few electrons? With 3 pi bonds in it, hopefully it's reasonably obvious that benzene is electron rich, okay, which means that benzene will be a nucleophile in any reactions that it does. So that means that we're going to be looking for reactions with electrophiles. So if we look at benzene and say, oh, well, we have 3 pi bonds. As we began to talk about last chapter, we might think that we can do an addition reaction the same that we would do to any alkene. But here is the problem. If I do this reaction, I end up with a dichlorocyclohexadiene, which has lost its aromaticity. And if you remember from the heats of hydrogenation, benzene is more stable than a cyclohexadiene. So there's no energetic reason for this reaction to happen because the starting material is more stable than the product. So this is not a good reaction. So now we have to look at other mechanisms and see what else could happen instead of that addition reaction. So if we look at this generic substitution reaction, we can say, again, benzene has electrons. It's going to react with an electrophile who wants them. So electrons will go from the benzene to the electrophile. So then we get an intermediate where the electrophile has added to one position of the aromatic ring. This carbon here has lost electrons as that electron pair moved up to form the new bond here to the electrophile. So that position has a positive charge on the ring. Now, if we bring along some kind of a generic base, that base can come over, remove the proton, which causes this electron pair to move back into the ring, back into conjugation, which reforms the aromaticity. Now we don't have an energetic problem with this reaction because we're aromatic at the start, we're aromatic at the end, and we haven't lost stability like we would in an addition type reaction. We can also think about whether or not this first step is likely. Why is this a good intermediate? Well, we have a positive charge on it, and we have 2 other pi bonds. Okay, so if I look at this, the entire molecule is not conjugated at this point because there's an sp3 hybrid where the hydrogen and the electrophile both are. But outside of that, the rest of the molecule is conjugated. So I will start with the same structure. Now there are resonance forms that we can draw of this structure by moving a pair of electrons. Which can cause the carbocation to move around the ring. So here's one more resonance structure. There's yet another resonance structure that we can draw. We can move this pair of electrons over to where the positive charge is. And now hopefully you can see with 3 different resonance structures that delocalize the charge. Now we've lost aromaticity, but still there's a reasonably stable carbocation intermediate that then the base can come and attack, deprotonate to cause our final product. So if we had to draw the resonance hybrid of this, we could draw it like this, with 3 partial positive charges and 2 pairs of electrons that are shared around the ring. So one of the things that's very interesting with this, and we'll see this much later as we see more reactions that happen in substituted benzenes, is if you look at where the charges show up compared to where the electrophile is. And if I look here, this charge is ortho to the electrophile. This one is para. And this one is also ortho until the base removes the proton. Now, one common mistake that students will sometimes make with these mechanisms is that they'll have the base come and grab this proton because they see the positive charge here. They know that positive charge has to go away. So this pair of electrons would come here. The problem is there's another hydrogen up here, and this is sp3 hybridized. So if I do that, I can't get aromaticity back. And what I would get is something like this, which is non-aromatic. There's not a full octet at this carbon, and it's not a stable molecule. So you cannot do that. So this reaction certainly can occur. However, one other important piece to point out is that this electrophile must be a very strong electrophile. Even though the intermediate is resonance stabilized, you still have lost aromaticity, so it's still going to be higher energy. So we need a very good electrophile, and that's what the next piece of this chapter is going to be about.